To introduce myself, I'm Ranjit Jebananda. I wear a number of hats for IBIPSA England. I'm one of the board members and also the editor of IBIPSA England's newsletter. And as for my profession, I work as a consultant engineer at Design Builder. Before I move on to introduce our speaker, allow me to mention that if you are not a member of IBIPSA England, you can become one for free, and we will keep you updated on the latest news, events, job opportunities, etc. And I'll soon post a link in the chat box if you want to become a member. And also during the webinar, if you have any questions, please post them in the Q&A box and not the chat box. So I repeat, please post any questions you may have on the Q&A box and not on the chat box, and we will try to answer as many as we can at the end. Now to introduce our speaker, we have Professor Ian Morrison. Ian is a professor in the Faculty of Engineering and Design at Carleton University in Ottawa, Canada. He was the president of IBIPSA World from 2010 to 2015 and is the recipient of IBIPSA's Distinguished Achievement Award in 2021. Over the past 3 decades, he has researched, developed, and validated models and simulation tools for buildings and energy systems. He is author of the textbook Fundamentals of Building Performance Simulation, and he co-founded and has served as the co-editor-in-chief of the Journal of Building Performance Simulation since its inception in 2008. So I'll now hand over to Ian and can start when you're ready.
Okay, thank you very much, Ranjit, and thank you for the opportunity to present today to BIPS England. What I'd like to do today is to provide some motivation or explanation of why I think it's important that we do more to teach the fundamentals of building performance simulation and learn the fundamentals. And I'll share with you some of the methods that I'm using for teaching this, which have been encapsulated in this textbook that Ranjit mentioned on the fundamentals of building performance simulation. And really, the methods that I've developed have been through trial and error for the most part. I've been trying to teach people how to use BPS tools for about 35 years, and some of the things I've tried didn't work so well. Some work better than others, and I've tried to learn from both the positive and negative experiences to develop these techniques. So BPS has changed a lot over the years. As users of tools today in 2024, we have the choice of some pretty sophisticated user interfaces to BPS tools. Many of you will be familiar with tools like ISVE, Design Builder, eQuest, Green Building Studio, etc. There's many tools, and most of them provide some pretty nice features in terms of characterizing building geometry, defining HVAC systems, and extraction of results. And some of these tools, developers make some claims that I think are probably a little bit on the ambitious side. You'll see quotations sometimes of things like virtually no experience in energy analysis is necessary to use our tool. We make building performance simulation easy, etc. And it's true that these tools have advanced things dramatically. I'll show you what things were like when I started using BPS over 30 years ago. It was mostly text-based input, so no graphical feedback in terms of building geometry, no help dialogues, etc. You basically had, this is from the Do2 program, one of the first tools I started using, where it was text-based input. You used a text editor on the computer, and you had to define keywords and parameters. So the spelling was important, the hyphenation was important, and you had to define these and refer to external documentations, big printed manuals, to understand what keywords like cool reset schedule would mean, for example. So things have come a long way. It's much easier to operate these tools today than it used to. But some things I think haven't changed that much. I like to quote a paper that was written by Linda Laurie back in the 1980s. So we're going back almost 40 years ago. She was one of the lead developers of the BLAST program in the US. And she pointed out that really it's the users of these tools that are the key to calculating things accurately. They are the biggest potential source of error. And I think the situation hasn't changed drastically, at least in this regard, since those last 40 years. I think it has become easier to operate BPS tools, but no easier to produce accurate or realistic results. I'll show you a few examples of why I argue that. This is an example. This is from my own teaching. So these blue bars here represent the results produced by students. So I've got 38 students that are producing some results here, and they're predicting the space cooling load of a building. And they're all working from a common set of specifications, common weather file, etc. And the green bar here is where I expect most of the results to lie. I'd say that's the correct region of results. And you can see that a few people did predict within the expected range, but lots of people over-predicted, lots of people under-predicted. But if you look at those 38 students, these were all brand new novice users. Never before had they used BPS tools. And they were exposed to BPS, and they had some basic training on how to operate tools. We used a couple of different tools in this example. And within 2 weeks, they were all able to push all the buttons and pull all the levers to get the tool to predict some space cooling loads. But as you can see, it wasn't easy for us to get accurate answers. And you could look at that and fairly say, these are beginning users. We don't expect them to have that much proficiency yet. Or maybe you'd say, I didn't teach them very well. But in any case, it's an example of where we show it's easy to operate the tool, not so easy to produce accurate results. But there's lots of examples of similar spreads in results that are produced by more experienced users. Here's one of the first documented cases, a study that was done by Électricité de France back in the 1990s. They took a tool, Clim 2000, that they were developing and supporting, and they had a dozen users work off the same set of building drawings and specifications to make some predictions. And every one of those users made some pretty significant errors. And the predictions were, there's a lot of spread in those predictions as well. Here's another example from California from about a decade ago. A dozen users who are professional BPS users. These are people who earn their living, or at least partially, from providing BPS services to clients. They were given a set of building drawings and specifications, and all asked to predict the monthly gas consumption, monthly electricity consumption. And the yellow line here is the correct result, or where we expect the result to be. So you can see that each of the users produced results that in most cases were substantially different than the expected results. Sometimes producing results that were several times the expected gas consumption, and significant differences in electricity consumption. So if you look back to this spread, here's the novice users, results are all over the map. Well, we could say something similar about these experienced users as well. Here's another example from an IEA research annex from close to a decade ago, where 21 teams who were mostly PhD students, postdoctoral students who had a certain proficiency or expertise in operating the simulation tools were asked to predict the performance of an actual building. And the dark line here represents the measured performance in that building. And you can see some of the users are predicting results that are similar to the measurements, but we've got a lot of spread in those results as well. So again, it's I think these examples go to show that it's really not that easy to use these tools to accurately predict building performance. And there's lots of good reasons why. Buildings are really complex. So in order to predict the performance of a building with a BPS tool, we've got to consider a lot of concurrent heat and mass transfer processes that are coupled together. And it means that we have to accurately characterize all of the significant processes, the passive solar gains, the air infiltration, the functioning of the HVAC systems, all the internal sources of heat and moisture. We have to be able to consider all of those factors that are significant in order to predict overall building performance. And I think it's quite easy for users to feel overwhelmed by this. In many cases, users might not know where they should be placing their efforts. They might not understand the implications of some of the assumptions they're taking, or some of the use of some default data. They might not even be aware that what default data their tools are using in some cases. They might not appreciate that there's optional methods supported by their tool, and that they could have an influence over the results by choosing between optional methods. And this is where I think it's important that we really underline the fundamentals of the tool. I think in many cases, we're training users to operate a piece of software without teaching them an understanding of the modeling approaches that are used underneath, what's happening under the hood, for example. They might not be familiar with the simplifications that are inherent in some of the models that are used. They might not understand the different modeling methods that their chosen tool is using. They might not understand which inputs are going to have the greatest impact upon results. So this is why I feel understanding the fundamentals is key. Whether it doesn't matter which simulation tool you're using, this kind of knowledge is transferable. You can use it in tool A versus tool B versus tool C. And once you have this level of understanding, it's relatively easy to pick up another simulation tool and to learn how to effectively apply that. So this is the motivation behind the approach to teaching BPS that I've developed over the years, and it's really the underlying ethos of the book that I've published on the topic. So basically, this book grew out of my teaching of courses at the university level and professional development level. So this book is really emphasizing the depth of BPS rather than breadth. It's not trying to cover all topics of BPS. It's really focusing on heat and mass transfer processes. It doesn't get into things like daylighting, for example. It also has some treatment of HVAC systems. And I've written this book and when I teach my course as well, I'm pitching it at a level where I expect the reader and the students to have some basic understanding of heat transfer and thermodynamics. So they've taken some undergraduate level courses at university, so they have the fundamentals of heat transfer and thermodynamics, a little bit of understanding of psychrometrics, and they're somewhat familiar with HVAC terminology and some common HVAC configurations, but they don't need to have any prior experience with BPS. And in fact, when I teach my course, or I guess module is the term more commonly used in the UK, most of the vast majority of the students have never touched a BPS tool prior to that study. So the book structure and the teaching approach I use is based upon 4 modes of learning that are interrelated. So the book is broken up into a number of topics. Here's topic 1 here, and there's topic 2. For each topic, the structure is similar. There's some theory that's presented. So this is describing how BPS tools will model a certain heat or mass transfer process. It's written in a tool agnostic way, so I'm not teaching them how the methods used by a particular tool, but showing the breadth of methods that are used by the various simulation tools that are currently in use. So they understand some of the theory, and then there's a set of simulation exercises that exercise that theory, that isolate that particular heat or mass transfer process. So the students will read the theory and then right away perform some structured simulation exercises. And when I teach this course, I have the students submit their results from their simulation exercises right away. And then the next time we meet at our next class, we do what I call a simulation autopsy. And that sounds a little bit gruesome, but essentially what we're doing here is we're dissecting the work that they've done to try and understand why one student predicts a certain result and another student predicts a different result. And we'll do that collectively. So we'll look at the results, and I'll often ask students to come up and plug in their computer and show their simulation input files. And then after performing that autopsy, I ask the students to go away and reflect upon what did they learn from the autopsy that enhances their understanding of the theory that was studied. And then in some cases, they might go back and repeat a simulation exercise. But we go around that that loop and those four modes of learning. And then once we complete that on a particular topic, one heat or mass transfer process, we then move on to the next topic and repeat the same kind of structure in the next topic. And I break this teaching down so that we are focusing on all of the significant heat and mass transfer processes that are happening. And we explore each one in turn, and we go through those four modes of learning, looking at the theory, running some simulation exercises, analyzing some results, reflecting. And the way I structure it in the teaching and in the book as well is the first portion of the book focuses on all the heat mass transfer processes happening in the indoor environment. So that would be internal heat and moisture sources, long wave radiation exchange between individual surfaces of internal surfaces of the building, convective heat transfer from an internal building surface to the zone air. And then after that, we'll focus on the heat mass transfer processes that are happening between the building and the external environment. So convective heat transfer to wind-driven airflow, long wave radiation exchange from external surfaces to the sky, to the surrounding ground surfaces. And then we look at heat and mass transfer processes happening through the building envelope. So that includes air infiltration, transient conduction through the solid materials, and solar transmission through window assemblies. And then following that, focusing on HVAC systems. So each chapter of the book follows a similar structure. It outlines some learning objectives, and then it introduces basic theories. And the level of theory that's presented depends very much on the heat and mass transfer process that we're studying. So it might just be a few pages, it might be 15 or 20 pages. Sometimes it gets pretty mathy, other times it's more high-level descriptions. So it depends upon the topic being covered. It treats the methods that are commonly used in contemporary BPS tools. So it's not written in a tool-specific way, it's written as tool agnostic. And it tries to point out the strengths and weaknesses of the different modeling approaches that are currently used. Sometimes it does get into the detailed mathematical descriptions, but I don't put math in unless it's really necessary to illustrate a point. And it's certainly not a comprehensive compendium of models. This is not an encyclopedia that you would turn to. It's really teaching the reader enough that they can understand the methods that are used in their selected tool. And if they really want to understand that in greater detail, they would have to go to a reference manual or an engineering manual for their particular tool. And in each chapter, there's a series of readings that are suggested. These are readings that are mostly from journal articles, conference papers, and it provides guidance on how to read these. So in some cases, it might say, read this paper in its entirety and look for these points in the paper, or read just the introduction to this paper and find answers to certain questions. And then it provides a number of sources for more detailed learning for those who really want to go into greater depth. And then, as I mentioned, every chapter topic has a set of simulation exercises. I'll give you some examples of the kinds of information that are given in the theoretical parts of the building. So I mentioned that students should, the reader of the book needs to have some basic understanding of heat transfer principles, but I don't expect a high level of graduate level knowledge of these topics. So on the chapter that explores radiation exchange, long wave radiation exchange between internal building surfaces, say a wall surface and a floor surface, it starts off by describing radiation emission from black bodies and gray bodies. It talks about the spectrum of emissions. And then it goes on to present the details of enclosure analysis. So a long way, this is not unique to buildings, but an enclosure analysis that could be used for long wave radiation exchange in gray enclosures. And it goes through the mathematical development to show how we could calculate the net radiation heat transfer between two surfaces. And it becomes apparent from that we need knowledge on radiation view factors between all the surfaces in the building. We need to understand, we need to have values on the long wave emissivity of all of the materials making up the internal surfaces of the building. And then it describes alternate methods that are used in some other tools. Here's an example of some of the theory that's given on talking about solar radiation that's absorbed by external surfaces. So it gives some basic description of things like solar angles and how we would calculate the incident angle between a building surface and the beam radiation coming from the sun. It talks about solar positioning. It then gets into how we calculate the diffuse radiation from the sky, the radiation that has been scattered by Earth's atmosphere as it's traveling between the sun and our building surface. And then it explains that all of the models that are used in BPS tools are empirical in nature. This is the well-known appraised model that's used in many simulation tools, but many people aren't aware, many users of these tools aren't aware that this is an empirical model that includes constants that have been tuned or derived based on measurements taken at particular locations. So it gives this level of theory for each one of these individual topics. And then there's always a series of exercises. And the first exercises are, all of these exercises initially in the teaching and in the book are based on some simple shoebox models initially, and then they progressively become more complex as the book progresses on. So there's a couple of shoebox examples, one that's has constructions that are more representative of low mass residential buildings, houses, and another one that's more representative of a higher mass office type construction. And these exercises are all written in a tool agnostic fashion. So you should be able to pick up any building simulation tool and run these cases. And they've been simulated with half a dozen or so different simulation tools to date, to my knowledge. And each of these simulation exercises are fairly short in description, and as I mentioned before, they're trying to isolate an individual heat and mass transfer process, and they're trying to illustrate what happens when we exercise some optional modeling methods, what happens when we change some inputs that are often uncertain, and we try to understand the implications of that on the calculated results from the simulation tool. So here's an example on the exercises related to the solar gains at internal surfaces. So here in one exercise, we're manipulating the solar absorptivity of the floor, the internal surface of the concrete floor, between two values, 0.6 and 0.9. So a fairly significant change. And here's an example of a result that was submitted by a student the last time I taught the course. And you can see this is a result plotted over one day. And you can see the orange line is the solar absorbed on that floor surface in the first case where the absorptivity was 0.6. And then when the student changed that value to 0.9, we see an increase in solar absorption by the floor surface. All makes sense. The students look at that, reflect upon it, and say, yeah, that makes sense. It agrees with the theory that I studied. But then we look for those same two simulations. We look, what's the impact on the heat addition by the HVAC system over the day, over that same day? And you can see those two simulation results are almost the same. And so I asked the students, reflect on that. Why is that we see a significant difference in the amount of solar absorbed on the floor surface when we make that change? That makes sense. But why does it not affect the amount of energy the HVAC system needs to inject to heat that building? And then we have group discussions around this, and I point the students back to look at the energy balances that were formed for the building. And what they realize here is that for at least this particular building in this particular climate, it didn't really matter so much which internal surface of that building absorbed the solar energy. Once it was inside the building envelope, it had pretty much the same impact on the zone energy balance, and therefore the amount of heat that was required from the HVAC system. So as they go through this, I want them to sort of accumulate their knowledge, build up their experience at using BPS and understanding the building physics as well at the same time. Here's another example of some of the exercises related to calculating air infiltration. And we're exercising different air infiltration methods. This is air infiltration is a topic that's treated very simply by many users of BPS tools. We often assume a constant air infiltration rate. Maybe we ignore it. And we're looking at, in these simulations, at the implications on space heating load from a couple of those simplified assumptions. And then another exercise where we employ a single zone air infiltration model and maybe network airflow model. And we can see that the impact of our choices as a user when it comes to modeling air infiltration are pretty significant. Again, at least in this building type and in this climate zone. And one of the things I want the students to take away from this is looking at that and say, well, air infiltration really matters to my simulation predictions. And I flip back here and look at solar absorptivity of internal surface. Nah, not so much. So as a user, where should I place my effort when I'm characterizing a building? Well, it's obviously more attention should probably be put on air infiltration than some other aspects. So there's a series of exercises like this. We go through and study the theory on each heat and mass transfer process at a time, run some exercises. People are accumulating knowledge as they go along. But these are all done on shoebox buildings, very simplified hypothetical buildings. We then put it all together into what I'm calling culminating trials, where we're now going to use a BPS tool to predict the performance of an actual building. And now we have to put together all of the knowledge that we've learned so far, how to treat air infiltration and solar transmission through windows and HVAC system performance, et cetera, et cetera. And I use, this is a research facility on our university campus. It's an unoccupied test house that we extensively monitor. So we have a lot of measured performance on that building. I provide photographs during the construction phase, so people can really understand the materials and the makeup of the house. There's building plans and specifications. There's site measured weather data. There's detailed measurements on internal sources of heat in that building. And based on all that information, my students in my course have to now apply a BPS tool that they're choosing to try to predict the performance of that building over a certain period of time. And it's great when the students take different approaches. I get lots of different approaches from the students, and here's a couple of examples from the recent offering of the course. Here's one student who used Design Builder, and she decided to faithfully represent the geometry as accurately as possible. So she's got every window assembly is a separate surface in her Design Builder calculation. She's represented all of the interior construction. So this is just a storage closet, a tool closet. She's got all the walls and the geometry of that shown accurately. Here's another student's work where they're using Transys, and they've chosen to abstract the geometry much more so than the first case. And in this case, he's using just 3 thermal zones, and he's lumped all of the windows together. And the advantage of students using different tools and different approaches is that when we share the results, they all learn from each other. So this student certainly spent much less time defining geometry than that student. But what are the implications of that? We get to see some of that when we share the results. So they go through this period of time where they're developing their building descriptions, they run simulations, and now we compare against measured results. So here's this blue line here on the left is showing some measured temperatures on a particular day. And all of the series plotted on the right are simulation predictions from individual students. And we look at this together and we then say, well, why did this student here with the red dots produce very different results than some of the students up here? And we try to understand, have some discussions around this. What happened here? Why do we have much lower temperatures predicted at night? And why does that building heat up much more rapidly and hit a higher peak temperature? So we want to understand what decisions did that person take. We're not pointing out errors here. It's about how do we learn from these results? How do we collectively learn from these results? So that's one of the examples where we're predicting temperatures. There's other trials where here's a free float example. There's no HVAC system in this case, and we're comparing now the measurements to a BPS result. Here's another trial period where we're looking for a longer period of time. We're trying to predict the amount of space heating that's required to maintain the set point temperatures in the building. So there's a lot of learning that happens when you apply BPS to a real building. It's a lot messier, of course. I think many of you will know that. It's a lot messier than than you think it ever will be. And there's lots of decisions that you have to take as a user. And it's interesting to learn what are the implications of some of these decisions. There's another culminating trial that this is actually in development right now. This will be included in the second edition of the book, which will be published in 2025. This focuses now on HVAC systems. So the first building is a residential scale, light, low mass construction, simple HVAC systems. Now we're looking at an air-based HVAC system. So we're focusing here on, this is an office space on the university campus, and we're focusing here on the top floor of that and the HVAC system that serves that top floor. So again, there's lots of photographs that are available that shows the atrium space in the building, the thermal zoning strategy for controlling HVAC systems. I provide detailed drawings and specifications, construction drawings that give detailed specifications. Wall cross sections, details the materials used in the wall constructions, and a schematic representation of the HVAC system. So the purpose of this trial is really to focus on the HVAC. So this is a fairly conventional air-based HVAC system with heating and cooling coils, a variable air volume system. Each zone is served by a VAV box and has a terminal hydronic heating system. So in this trial, we're really trying to focus on, can we predict the performance of the economizer cycle, the operation of the outdoor and recirculation dampers? Can we predict the operation of the heating and cooling coils to predict the supply air temperature? Can we accurately predict the functioning of the VAV boxes, the airflow through the VAV boxes, the operation of the hydronic terminal units? So I'm going through this exercise right now with a group at IES. And we're sort of midway through this right now. But again, the approach is similar. We're comparing measurements to simulation predictions. So we have some cases here where we're using these results to verify that the building model that has been developed accurately, where we're treating the HVAC in an idealized manner, and we're comparing building loads to measurements. And we're now at the stage where we're looking at things like the functioning of the economizer cycle. Can we correctly predict the outdoor air fraction? Can we correctly predict the mixed air temperature, the supply air temperatures, et cetera? So in the second edition of the book, this will be included. The feedback I got from a number of people who have used the first edition of the book is that they wanted more treatment on HVAC systems. So that's the major addition area in the second edition of the book. So to sum up, this book that I've talked about today is really developed out of the teaching that I've been doing at Carleton University for the last 15 years. And that teaching really evolved out of teaching I did, practicing architects, engineers for about 15 years before that. And like I said, I've tried to learn from all my mistakes and work on these teaching methods. And I feel very strongly that we need to better equip users with an understanding of the fundamentals of what the tools are doing. Figuring out how to operate the tools is going to come pretty easily after that. This book has been used in a number of university courses and professional development courses. I'm trying to learn from the feedback I'm getting and improving the content for a second edition. So it was first published 4 years ago. I've got a few months to wrap up the second edition, and that will be published in early 2025. And as I mentioned, the major additions to that, the second edition is going to be on treatment of HVAC systems, but there'll be additional simulation exercises. The feedback I keep getting from my own students and others who have used the book is that they find the simulation exercises to be one of the most valuable parts of the learning. And again, it's a tool agnostic book, and it's something that's been endorsed by ABIPSA. I'm very happy about that. And I'm planning the second edition to be endorsed by ABIPSA as well. So if you're curious about more on the teaching approach, happy to answer questions here. But if I can't get to some of that, there's a couple of articles that you might want to refer to. One of them is an article that I published in the Journal of Building Performance Simulation a number of years ago, about 5 years ago, and a more recent, shorter article that was published in the RIVA journal last year. So with that, I'm happy to take any questions that people have or listen to your feedback.